Welcome back to Discrete Math. I'm Dr. Jeff Groh. Today we're going to talk about primes and greatest common divisors. Primes are, of course, very important in cryptography, as anyone who has studied the subject understands well. People often generate primes having a huge number of digits, and often pairs of primes not very far from each other on the number line, and products of those pairs yield certain interesting algorithms for cryptography. So what is a prime? First of all, it's a number p in the natural numbers. P strictly greater than 1. We're not going to allow 1 to be a prime. The reason being that in more complicated spaces besides the real numbers, we still want to have some notion of prime, but we don't want these primes to equal what are called units. There are different units in the complex plane, for instance, and we can always divide out by a large number of these so-called units. In any case, in the real numbers, we have this one unit, 1. Negative 1 might also be considered a unit in some ways, but in any case, a prime is a number p, element of the natural numbers, p greater than 1, such that the only divisors, these are numbers that divide evenly with remainder equal to 0, of p are 1 and p itself. An example of a number that's not prime, 6 is 2 times 3. So 6 is divisible by 2 and 3 as proper divisors, which means 6 is not prime. From the example of the number 6, any number that is not prime is said to be composite. However, let's look at another example. 2 is prime because 1 divides 2 and 2 divides 2, but there's nothing else that divides evenly into 2 with a remainder of 0. What about 3? 3 is 1 times 3. The only things that go into 3 are 1 and 3. What about, well, 4 is not. 4 is 2 times 2, so it is composite and not prime. What about 5? 5? The only things that go into 5 are 1 and 5, so it's prime. 6 is, of course, not, as we mentioned before. It's 2 times 3. 7 is a prime. But 8 is not. 8 is 2 times 4, or 2 times 2 times 4. But, and 9 is not a prime because it's 3 times 3. 10 is not a prime. It's 2 times 5. But 11 is a prime. 13 is a prime. 17 is a prime. 19 is a prime. These are all primes. There are a large number of primes. Make a special note. 1 is not a prime. Yes, it is only divisible by 1 and itself 1, but 1 is a unit. And so it's not a prime, it's a unit, and we're not going to consider units to be primes. Remember, numbers that are not primes are composite. If n is not a prime, then it has to be divisible by something between 1 and n. There exists some number, let's say a, bigger than 1, less than n. It's a natural number such that a divides evenly into n with a remainder, of course, of 0. We now introduce the fundamental theorem of arithmetic, which says that every number n that is an element of the set of natural numbers n strictly greater than 1 can be uniquely expressed as a product of powers of primes. So this is an existence uniqueness theorem that can be expressed, and it can be expressed in that way uniquely. As an example, 12 is 2 squared times 3. We're expressing 12 as a product of powers of primes. The implied power on the 3 is, of course, 1. What about something like, say, 25? Well, that's 5 squared. How about 18? That's 2 times 3 squared. Every natural number greater than 1 can be expressed uniquely, in only one way, as a product of primes. So if I have a number n, it can be expressed as prime 1 to the power k1, prime 2 to the power k2, prime, let's say, m to the power km. And what is unique will be the primes that are used and the powers, the exponents that occur. There's no other way to factor 12 other than 2 squared times 3, expressing it as a product of powers of primes. The following theorem is very useful in helping us figure out the prime divisors of a particular number. If n is an element of the set of natural numbers n strictly greater than 1, and n is composite so that it is not prime, then n has a prime divisor p such that p is no greater than the square root of n. This is a very important theorem. For one thing, let's suppose you're looking for the divisors of n. You want to test, perhaps, whether or not n is prime. Well, you don't have to check primes very big. The biggest prime you have to check might be the square root of n. And if you don't find a prime divisor after testing numbers 1 through the square root of n, then you can be sure that that number is not composite. The hypothesis must be false, and the number must in fact be prime. So let's look at some examples. Consider n equals 100. Then we're looking for prime divisors less than or equal to the square root of 100, or 10. Can we find any prime divisors less than that? Well, sure. 2 divides 100. 2 squared, in fact, divides 100. 5 divides 100. And so if we're looking for the primes that divide 100, we found them both, 2 and 5. These both divide 100. And they're both smaller than the square root of 100. In other words, namely 10. In the next example, let's look at n equals 101. The square root of 101 is certainly less than or equal to 11. 11 squared would be 121. So that means in order to check to see if 101 is prime, you only have to look at the primes smaller than 11, strictly smaller than 11, because square root of 101 is strictly less than 11. So what are the primes less than 11? Well, those are 2, 3, 5, and 7. Those are the only primes we have to check. Well, 101 is not divisible by 2. It's not divisible by 3 either. If you divide, you'll have 3 times. 3 goes into 10 with the remainder of 1. It goes into 11 3 times with the remainder equal to 2. And so the fact that the remainder is not 0 means that 3 is not a divisor. It's clearly not divisible by 5. And how about by 7? 7 goes into 10 once with a remainder of 3. It goes into 31 4 times, but it'll have a remainder of 3 there as well. And so, since that's true, this is not a divisor. We may conclude that 101 is a prime. If it were composite, it would have to have a prime divisor less than or equal to the square root of 101 itself, and it doesn't. In our proof, we get to assume that n is composite, which means we'll let n be a times b. These are natural numbers, not equal to 1. And so n will be composite. It'll be expressible as a product of natural numbers that are not units. Now, if a and b greater than the square root of n, if they're both bigger than the square root of n, then a times b will be bigger than n and not equal to n, and that's a contradiction. Thus, at least one of these factors, one of a or b, is less than or equal to the square root of n. Note that we haven't said whether or not a or b is a prime. In fact, they might neither be a prime. However, we can say this without loss of generality, which is often abbreviated by W log in mathematical circles. Suppose that a is the 1. One of them has to be. Let's let a be. Then there are only 2 possibilities. Either a is prime, in which case we're done proving the theorem, or by the fundamental theorem of arithmetic, a has a prime divisor p. So if a has a prime divisor, if p divides a and a divides n, then p divides n. And that means p has a prime divisor. What is more, p is less than or equal to a, and that's less than or equal to the square root of n. So that prime will be no bigger than the square root of n. That's the end of the proof. An immediate corollary to this last theorem is that if n is in n greater than 1, and n has no prime divisors less than or equal to the square root of n, then n is prime. As an example, I'm going to ask, is 129 prime? Well, we only have to check the prime divisors less than or equal to the square root of 129, and that's certainly less than 12. So the only primes we have to check are 2, 3, 5, 7, and 11. We can knock a couple of these off our list right away. This number is odd, so it can't be divisible by 2. The digit sum, notice that the digit sum 1 plus 2 is 3, plus 9 is 12. 12 is the digit sum, and if you add those two together, you get 3. That implies 129 is divisible by 3. 3 goes into 12 4 times, no remainder. 3 goes into 9 3 times. So 129 is 3 times 43. So the answer here is no. Is 131 prime. Again, we only have to check primes up to 12, or 2, 3, 5, 7, and 11, in order to determine whether or not this number is prime. Again, it's not divisible by 2. In this case, the digit sum is 5, and that's not divisible by 3, which means this number is not divisible by 3 either. It's not divisible by 5 because the units digit is not either a 0 nor a 1. So is it divisible by 7? 7 goes into 13 once with a remainder of 6. 7 goes into 61 8 times, but 7 times 8 is 56. It's going to have a remainder of 5. So we can cross 7 off of our list. Numbers in the hundreds range will be divisible by 11 if the sum of the first and last digit equals the middle digit. And that's not true here, so this number is not divisible by 11. We could also check it just by dividing. And we get a non-zero remainder, and so it's not divisible by 11. So is 131 prime? Yes. We don't need to check any more primes. You only have to check primes up to the square root of the number itself. Find the prime factorization of 7007. The prime factorization of 12 is 2 squared times 3. We're looking for a similar decomposition of this number. 7007 is clearly 7 times 1001, where 7 is a prime. Now, what are the factors of 1001? We only have to check for divisibility by primes up to the square root of 1001, and that's rounded 31.6, so we only have to check primes up to 31. So what are those primes? 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and 31. So we'll just check these numbers and see if we can get something in between there that divides 1001. Clearly 2 is off the list, 5 is off the list, 1 plus 1 is 2, so 3 is out. Does 7 go into here? 7 goes into 10 once with a remainder of 3. It goes into 30 4 times with a remainder of 2, and then 7 goes into 21 3 times with a remainder of 0, which means 7 is also another factor. That means 7007 is in fact 7 squared times 143. We just need to figure out the factorization of 143. Notice that 1 plus 3 is 4. That's a key indication that 143 is divisible by 11. So let's look at 143 divided by 11. 11 goes into 14 once with a remainder of 3, and 11 goes into 33 13 times. We now see that 7007 is 7 squared times 11 times 13. And this is the prime factorization of 7007. We're now going to look at the famous sieve of Eratosthenes. This is a way of finding primes. Suppose we're trying to find primes up to 13. The first number you encounter that hasn't been eliminated is a prime. 2 is a prime. But let's look at all of the other multiples of 2 and cross them off of the list. This is the first phase of sifting. The next number you can encounter will be a prime, but you have to cross off all those that are divisible by that number. And then the next number will be a prime. But then you cross out all those divisible by that number. The number after that will be prime. No more 7s to cross out. 11 is prime, and 13, these are all primes. So if I'm working on an expanded list, 2, 3, 4, 98, 99, 100, 2 is a prime, and then cross out all the even numbers after that. 3 is a prime, and that crosses this one out. And that's how you proceed. Cross out all multiples of 3. The next uncrossed out number will be a prime. Take that, divide, cross out all of the others divisible by that number after that. If all the numbers divisible by 5, from 5 to 100. And so you'll cross out 10, 15, 20, 25, and so on all the way up to 100. In this way, we can arrive at a list of primes in some specified range. And now for a famous theorem. There are infinitely many primes. This is famous for a number of reasons. It's a very elegant proof by contradiction. Or reductio ad absurdum, which means that you assume that there are finitely many primes and then try to arrive at a contradiction. Suppose our complete list of primes is P1, P2, through some Pn. Suppose these are all the primes there are in the universe. Now the proof is somewhat constructive because we're going to set P hat to be the product of all of these, which is not prime because it's divisible by all of these, plus 1. The product of all of these complete list of primes, plus 1. Now, P hat must be composite, because if it weren't composite, it would be prime, and it's not in this list because it's bigger than all of the numbers in this list. So in fact, if this is a complete list of primes, and this is not in that list, then it must be composite. Thus, P hat is divisible by some prime less than or equal to P hat, or strictly less than P hat, since we know that P hat itself is supposed to be composite. However, the remainder, when dividing P hat by any of the listed P sub k's, the remainder is 1. It'll go evenly into this part and have 1 as the remainder every time. P is expressible as one of these primes times the rest of the primes, which we'll call Q, the quotient, and 1 will be the remainder. So none of the primes that we have, and we're supposed to have a complete list of primes, divides P, which means that P hat is prime. And that's a solid contradiction, because P must be composite, and yet it must also be prime. Where did the error in logic come? It came when we assumed that we could make a complete and finite list of primes. Therefore, the number of primes is infinite. And that's the end of the proof. Next, we present the following theorem. It's the prime number conjecture. And it begins by introducing a notation. Let P of x be the number of primes less than or equal to x. So pi of x is the number of primes less than or equal to x itself. Then pi of x is asymptotically equivalent to x divided by log of x, i.e., if we take the limit as x goes to infinity, a pi of x divided by the quotient x over natural log of x will get 1. We're next going to discuss greatest common divisors and least common multiples. We'll begin, of course, with a definition. Suppose m and n are natural numbers, not both 0. The greatest common divisor of m and n, sometimes called the GCD, is denoted by GCD of m and n, and is the largest integer that divides them both. The largest integer, d, such that d divides m and d divides n. Let's do a quick example. Suppose we're trying to find the greatest common divisor of 4 and 6. Well, they're both divisible by 2. And that's the biggest thing that divides both. Let's find the GCD of 24 and 36. What's the biggest natural number that divides both 24 and 36? Well, the answer here is 12. 12 goes into both, and that's the biggest thing. What's the greatest common divisor of 17 and 22? Well, in this case, the greatest common divisor will be 1, because that's the biggest natural number that will divide them both. After all, 17 is prime, so it's only divisible by 1 and 17, and 17 certainly doesn't go into 22. So the answer is 1. This gives us a chance to define a new concept. We say that m and n are relatively prime if the greatest common divisor of m and n is 1. As an example, consider the greatest common divisor of 14 and 25. Well, the prime decomposition of 14 is 2 times 7, and the prime decomposition of 25 is 5 squared. Since these prime decompositions share no primes in common, the greatest common divisor will be 1, and these two numbers are relatively prime even though neither of those two numbers is prime. More generally, we say that a list of numbers, m1, m2 through mn, are pairwise relatively prime. If the greatest common divisor of any pair of these, mi and mj, is 1. For all I not equal to j, and I and j coming from our list of indices here, 1 through n. As an example, consider the list 10, 17, and 21. Notice the prime decomposition of 10 is 2 times 5, and 21 is 3 times 7. These don't share any prime factors in common, so they are relatively prime. 17 is a prime, so it'll be relatively prime to either of these others. And so the list is pairwise relatively prime. Suppose we're trying to find the greatest common divisor of 120 and 150. The way to begin is looking at the prime decompositions of 120 and 150. 2 goes into here, but so does 4. But even 8 goes into here, so at least 2 cubed. How many times does 8 go into 120? It goes in there once with the remainder of 4, and it goes into 40 5 times. So the prime decomposition is going to be 2 cubed times 3 times 5. Now, what's the prime decomposition of 150? Well, it's 2 times 75, and that's 2 times 3 times 5 squared. So if we're looking for the greatest common divisor, what we'll do is we'll look at the common prime factors, and we'll take the smaller of the two powers. So the GCD that we seek should be 2 to the 1, 3 is common to both, 3, and then 5, and the smallest power there is 1. So 30 will be the greatest common divisor. We now turn our attention to the least common multiple. Here we're going to say LCM of m and n is the smallest natural number, or integer, greater than m and n, such that smallest integer, we'll call it big M. M divides big M, and n also divides big M. So big M is going to be the number that is the smallest number bigger than, the minimum number bigger than or equal to m and n, and m divides big M, and n divides big M as well. Let's do a quick example. What's the least common multiple of 6 and 15? It also is helpful to look at the prime decompositions in this case. 6 is 2 times 3, and 15 is 3 times 5. In this case, when we're looking for the least common multiple, we take the maximum power that appears. In this case, the LCM will be 2 times 3 times 5, or 30. In the next theorem, We're going to take m and n to be elements of the set of natural numbers, by which I'm assuming 0 is not a natural number. Then m times n will in fact be equal to the greatest common divisor of m and n times the least common multiple of m and n. Let's look at an example. Suppose I'm looking at 4 and 6 as my numbers. We know 4 has the prime decomposition 2 squared and 6 has the prime decomposition 2 times 3. So the greatest common divisor of 4 and 6, we look at the minimum powers, and the minimum power on 3 is 0. So the greatest common divisor will in fact be 2. What about the least common multiple? There we look at the maximum powers. There, the maximum power, 2 squared, and here's 3. So 4 times 6 is 24. Is that the same thing as 2 times 12? And that's true. So we can see that it was, in fact, the greatest common divisor times the least common multiple. We're now going to look at something called the Euclidean algorithm. This gives us a more efficient means of finding the greatest common divisor besides prime factorizations. I'll show you how this works by illustrating an example. Suppose we're looking for the greatest common divisor of 91 and 287. The way this begins is by doing a division. 287 divided by 91. So how many times does 91 go into 287? Well, it goes into 287 3 times. That would be 273. We'll have a remainder when we subtract 287 minus 273, that gives us a remainder of 14. Aha! So that means that 287 is 3 times 91 plus 14. So we can break 287 up into these two pieces. Now, if n divides 91 and n divides 287, if it goes into both, then it has to go into here. It goes into 91 evenly, which means that it also has to go into 14. It goes evenly into 287 on this side, divides it as an integer times n, whatever it is. We know n goes into 91, so it goes evenly into 3 times 91. And since it goes evenly into this and evenly into this, it has to evenly go into 14. So that common divisor has to be less than or equal to 14. Is 14 the greatest common divisor? I don't know, but what we can do is say the GCD will discard 287 and take the smaller of these two, 91 and 14. The GCD that we seek will be the GCD of 91 and 14. That's a much smaller problem. We'll do the same trick though. We'll take 91, the bigger of the two, and we'll divide it by the other. How many times does 14 go into 91? Well, it goes in 6 times. 60 and 24 makes 84, and 91 minus 84 gives us 7. So the remainder is 7, which means we can now just look at the GCD of 14 and 7. 7 being prime and 14 being divisible by 7, we see that the answer is 7. So there's a kind of winnowing process. We divide and get a quotient and a remainder. We forget about this part. The number that we're seeking that divides both 91 and 287 will have to divide 14. So we'll replace the bigger one with 14. We'll divide again. We'll get another remainder. We'll throw away the bigger number, and that gives us two easier numbers to compare. At some point, the answer will be obvious. We have the following lemma. Let M, N, Q, and R be elements of the set of natural numbers, and in particular not zero. And also suppose that N is Q times M plus R. Then the greatest common divisor of M and N will equal the greatest common divisor of M and R. In the proof, we show that common divisors of M and N are common divisors of M and R. So let D divide M and D divide N. What does that mean? That means that M is K1 times D and N is K2 times D. K1 and K2 are elements of the set of natural numbers. There has to be some natural numbers so that we get this kind of product. Then since we have N is Q times M plus R, we'll have N, which is K2 times D, equals Q times K1 times D plus the remainder. Which means then, if we move this over, we get R is K2D minus QK1D. D being a common factor, we can rewrite this as K2 minus QK1 times D. That means D divides R. The only thing left to check is if the common divisor issue goes the other way around as well. Do the common divisors of M and R, are those also common divisors of M and N? If D divides M and D divides R, then M is K1 times D and R is K2 times D, which means N, which we know is Q times M plus R, will be Q times K1D plus K2D. We'll have these two terms, both of which have a common factor of D. We can factor the D out and assume then that D divides N. So common divisors of M and R will be common divisors of M and N. So the implication goes both ways. That means we deduce then that the greatest common divisor of M and N has to be the same as the greatest common divisor of M and R, because both pairs have the same divisors, so they'll have the same greatest divisor. As an example, suppose we're looking for the greatest common divisor of 414 and 660. Well, how many times does 414 go into 660? It only goes in there once. What do you get as the remainder? You'll have to subtract. And it looks like you'll get 246. And so this will be the same as the GCD of 246 and 414. Well, we do the division process again. And again, it goes in there once. What's the remainder when I subtract? 168. Let me check. 300, 414. That's right. So this will be the same thing as the GCD of 168 and 246. And so we go again. How many times does 168 go into 246? It goes in there once. So what do you get when you subtract? We'll have to borrow. Let's see, we'll have to borrow. 16 minus 8 is 8. 13 minus that is 7. We've already borrowed, so 78. So we get the GCD of 78 and 168. So how many times does 78 go into 168? Well, it goes in there twice, 140, 156. 168 minus 156 is going to be 12. And so we'll get the GCD of 12 and 78. So how many times does 12 go into 78? It goes in there 6 times. I mean, 60 and 12 is 72. The remainder is 6. So we get the GCD of 6 and 12. 6 goes evenly into 12, so the GCD will be 6. You'll probably see that we could have figured out 6 goes into each of these pretty easily. The digit sum here, 4 plus 1 plus 4, is 9, so this number is divisible by 9, and in particular by 3. 660 has a digit sum of 12, which is divisible by 3 but not by 9. So 3 will have to be a factor of the greatest common divisor. But they're also both divisible by 2. So you know 6 goes into at least both of these just by looking at them pretty cursorily. Next, a linear combination of integers m1, m2 through mn is an expression of the form c1m1 plus c2m2 plus plus cnmn, where each of these c sub k's will be integers. So all of the m's are integers, and all of the coefficients are also integers. So a linear combination is just a simple sum in this form. One thing to note is that the greatest common divisor of m and n is a linear combination of m and n. To see this, let's look at an example. Let's look at the greatest common divisor of 6 and 14. Well, the prime factorization of 6 is 2 times 3. 2 goes into 14, but 3 doesn't. So the greatest common divisor is 2. So are there integer constants, coefficients, c1 times 6 plus c2 times 14 that give you 2? And the answer is yes. We'll let c2 be 1 and c2 be negative 2. Negative 2 times 6 is negative 12, plus 14 is 2. So 2 is, in fact, negative 2 times 6 plus 1 times 14, expressing 2 as a linear combination of 6 and 14. Bézout's theorem codifies this. If m and n are elements of the set of natural numbers, then there exists c1 and c2 in the set of integers such that the greatest common divisor of m and n is c1m plus c2n, so that the greatest common divisor is always a linear combination of the numbers going into it. You'll notice that typically one of these numbers is going to be negative and the other positive. This equation is called Bézout's identity, and the coefficients c1 and c2 are Bézout's coefficients. In our next example, I want to express the GCD of 198 and 252, which is otherwise known as 18, as a linear combo of 198 and 252. And the way that we're going to solve this problem is to go through the Euclidean algorithm, do the divisions, and then work things backwards from there. So how many times does 198 go into 252? Well, it only goes in there once. We'll have to borrow 12 minus 8 is 4. We'll have to borrow again. 14 minus 9 is 5. And so we get a remainder of 54, which tells us then that 252 is equal to 1 times 198 plus 54. Now we'll find the GCD of 54 and 198. And we'll do it the same way. We'll take 54 into 198. This clearly goes in there 3 times. 150 plus 12 is 162. Subtract, we'll get 36. So we get that 198 is 3 times 54 plus 36. So now we're going to look at the GCD of 36 and 54. 36 goes in there once, and we'll have to borrow. We'll end up with 18. So that 54 is 1 times 36 plus 18. The last time we have to do this is the next time. We're looking for the GCD of 18 and 36. Well, 18 goes into 36 twice with a remainder of 0, which means 36 is 2 times 18. Now 18 can be factored out of everything in sight by making the substitution back in. We get 54 is 1 times 36, which is 2 times 18. So that's 3 times 18. So we'll now work this backwards. 18 is going to be 54 minus 36. But wait a minute, 36 is 198 minus 3 times 54. And if we do the combination there, we'll have negative 3 plus 1 is 4 times 54 minus 198. And then one more substitution, this time for 54. 54 is 252 minus 198 minus the 198 that's already there. So that's 4 times 252 minus 4 minus 1 is minus 5 times 198. So 18, the greatest common divisor, is 4 times 252 minus 5 times 198. We can even check the arithmetic in our heads. That's 800 plus another 200, that's 1,008. And we're subtracting 500 plus 450, that's 950, plus another 40, that's 990. So 1,008 minus 990 is going to be 18. Our next theorem is a lemma. A lemma is a theorem that you use to prove other theorems. Let's suppose m, n, and p are natural numbers, not zero. And let's also suppose that the greatest common divisor of m and n is 1, so that they are relatively prime. Then if m divides n times p, we know m doesn't divide into n, so m has to divide p. So in our proof, if the greatest common divisor of m and n is 1, then 1 is a linear combination of c1 times m plus c2 times n. For some integers, c1 and c2. We multiply everything in sight by p. So that p is c1pm plus c2pn. One of the hypotheses of the theorem is that m divides p times n. And that implies p times n is some integer k times m. If that's true, we can plug that in down here. We have p times n over here. We have c1pm plus over here c2pn is k times m. And you can see then that we get c1p plus c2k times m. Therefore, m divides p. Here's another lemma, and this one even more obvious. If p is prime, and we're assuming, of course, p is an element of the set of natural numbers, if p divides a product of integers mk, all of these elements of the set of integers, if p divides that product of integers, then p must in fact divide one of those. It's a prime after all, and so it has to go in one of those. It could go in others, but it has to go in at least one of them. We next give an important theorem. The prime factorization of any n in the set of natural numbers is unique. Like with many uniqueness proofs, you suppose that there are two ways of doing something and then show in fact that they are equal. Suppose n is p1, p2 through pn, and also n is q1, q2 through qk. We're not assuming they're the same number of primes, where each of these is a prime. We could have the same prime listed multiple times in the list. We're not using the powers just for convenience. But at least each of these factors is a prime. And without loss of generality, we'll assume P1 is less than or equal to P2 is less than or equal to PM. They go in increasing fashion. Same thing with the Q's. Next, we're going to eliminate all duplicates in each list. We know that these products are the same. If they have common terms, common factors, we can cancel the common factors off. So not all of these factors on each side are going to be left. We'll have Pi1 times Pi2 times let's see, what should we call it? S will be equal to J1, J2 to JT. So we'll have some different lists that share nothing in common, no prime factors. These have no prime factors in common. But as you can see, Pi1 divides the left-hand side, and that means Pi1 has to divide the other side as well. But by our last theorem, that means Pi divides one of these. Q, J, R for some R. This prime divides that prime, which means they're the same, which means this list wasn't reduced. Unless, of course, we end up with just 1 equals 1, in which case the factorizations are the same. This is a contradiction because these have to be distinct. All of these different primes have to be distinct. We've already canceled out all of the duplicates. And so that completes the proof. Note, 14 is congruent to 8 mod 6, but 7 is not congruent to 4 mod 6. The moral of this story is that you cannot divide common factors on each side of modular arithmetic. However, if you have some number k that is relatively prime to the modulus, where m is the modulus, if that's 1, so that they're relatively prime, then you can divide each side of a modular equation like this by that number k, but it has to be relatively prime to the modulus. 2 is not relatively prime to 6, because 2 goes evenly into 6. So the theorem looks like this. If A times D is congruent to B times D mod M, and the greatest common divisor of D and M is 1, so that they're relatively prime, then A will be congruent to B mod M. In our proof, we assume AD is congruent to BD mod M. And that implies M divides AD minus BD. And so M divides D times A minus B. Now, since the greatest common divisor of M and D is 1, M can't go into D, it has to go into A minus B. But what does this mean? That means A is congruent to B mod M, and that's the end of the proof.